Hello everybody. Alright, so we're going to be talking in this video about the content covered in chapter 12.1, which is all about sequences. And the first thing that we need to talk about when we're discussing sequences is what is a sequence? Um, so I'm going to give you two definitions, two sort of ways of representing sequences, and then we'll show that they're equivalent. Okay? So our first definition of a sequence is just going to be an ordered set of numbers. And we'll say real numbers here. All right? We're not going to talk about any other numbers in our sequences. All right? So an example of something like this would just be something along the lines of we can take A1, A2, A3, A4, A5, on and on and on. So in this case, each of the A sub a number is just an element of our sequence, and we know which order they come in because we just start from the left, go to the right. Lower numbers come before higher numbers, right? An example, like a real example, right, might be something like 1/2, 1/3, 1/4, right? We know which order they're in because we just lead left to right, and each one is a real number, okay? Our second definition, actually, let me give one more example. Something like this, just 1 0 1 0 1 0 1, right? This can also be a sequence, right? We can have duplicates. We can go back and forth. We don't necessarily need to be going in a specific order. There's lots of different things that we can show that are sequences, right? It just has to be a set of numbers that are ordered, all right? So our second definition is going to be a sequence is a function, and it's going to be a function A that takes us from the natural numbers. So that's things like 1, 2, 3, on and on and on, and it takes them to the real numbers. Okay? And an example of something that would do that would be something like A of n is equal to n squared minus 1. And so A of n equals n squared minus 1. That's a function. We can put natural numbers into it. It's going to give us real numbers out of the other side. And we can see there's sort of a similarity between how we're labeling our numbers here and the fact that we're putting in these natural numbers here, right? They're sort of, our natural numbers are labeling the elements of our set in both cases. In this case, it's the input of our function that's labeling each output. And before, we were just annotating and letting each of our A's have a subscript that's labeling it and placing it in the order, right? So we can take something that's written out as an explicit formula as a function from n to r, and we can write it as just our ordered list of numbers, right? So in this case, we'll start with when n is equal to 1 will be the first term in our sequence, right? So we'll say this is n, 1, 2, that's not a 2, 2, 3, 4, on and on and on. And then our a of n is going to be, in this case, a n of 1 is 1 squared minus 1. It's going to give us 0. 2 squared minus 1 is going to give us 3. Our 3 squared minus 1 will give us 8. And then 15 is going to be our 4 squared minus 1. Right? And on and on and on. We just keep following the pattern. Okay? So each one of these is our a of n, right? The function a applied to n, or our a sub n are going to be the same thing. Okay? We can also, for instance, we can look at this function right here. I'm going to call this star, this sequence here. and we take star, and we can find a function that's going to describe it. Right? So before, with our star, we had 1, 1/2, 1/3, 1/4, right? And we can see the natural number that is that term is in each of the terms, right? We've got 1 over 1, or 1 over 1, we've got 1 over 2, we've got 1 over 3, we've got 1 over 4. So when we want to describe this using a function, we can take a of n, and we'll just let that be equal to 1 over n, right? So any number n that you can think of, any natural number n, we plug that in, and we will find the nth term of this sequence if we continued the pattern that we started here. We can also find patterns for different kinds of sequences. So let's look at a little bit more complicated of an example. We'll take the sequence to find 1/3, -1/9, 1/27, -1/81, dot, 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 right? So the dot, dot, dot meaning we're just continuing the pattern that we started here. And we want to find an explicit formula for this. So we're going to start by finding the prime factorization of the denominators for each of these terms, all right? So we have 1/3, we've got -1 over 9 is 3 times 3, so we get 3 squared. We've got 1 over 27, which is just going to be 3 cubed, and then we have -1 over, it's going to be 3 to the power of 4. 3 times 3 is 9. That squared again is going to be 81. So there's two different patterns that we can see that makes up this sequence. The first thing that we notice is as we move from term 1 to term 2, we're getting an extra power. We're adding 1 to the power of our 3 in the denominator, right? We start with 1 over 3, then we get 1 over 3 squared, 1 over 3 cubed, on and on. So when we're writing out our function that explicitly describes this sequence, we're going to start with 1 over 3, and first term has 1 power of 3, second term has 2, on and on. So we're just going to raise it to the power of n. Now the other thing that we can see here is that it's flip-flopping back and forth between negative numbers and positive numbers. When we're looking at our nth term, right, when n is even, right, so this term, on and on, when n is even, a of n is negative. And when n is odd, right, so our first term, our third term, our a of n is going to be positive. So what I'm going to do to represent that in our explicit formula is I'm going to take a -1 out front, and then I'm going to raise it to a power that's related to our n, but makes it so that when n is even, a of n is raised to an odd power, and when n is odd, a of n is raised to an even power. Okay, so if I just took the n, let's just take and raise it to a power of n here, right? When we take -1 and we raise it to the power of 1, we would get a negative here. And then if we took -1 and raised it to the power of 2, then we would get a positive. And then if we raise it to the power of 3, we'd get a negative, positive, right? This is the wrong sort of flip-flopping that we're looking for, right? We want a positive in our 1 spot and a negative in our 2. So in order to compensate for that, I'm just going to add a +1 to the exponent there. So whereas before we were getting negatives where we should be getting positives and positives where we should be getting negatives, now when we raise it to the appropriate power, the nth power +1, we'll get the correct sign out front. Right? So let's just check really quick and make sure. So when we plug in 1 to our a here, our a of 1 we're going to get negative 1 raised to the power of 2 times 1 over 3 to the power of 1, which should give us 1/3. And that's exactly what we were looking for. If we look instead at a of 2, we're going to get negative 1 to the power of 3 times 1 over 3 squared, which will give us negative 1/9. And we can see that if we continue this pattern, we've described sufficiently what that sequence is going to look like. All right, so one more kind of way that we can describe sequences is going to be what we call recursively defined sequences. So what makes a sequence recursively defined is that the nth term is going to depend on one or more of the previous terms of the sequence. So an example might be something like this. Right? We know what the nth term of the sequence is, or a of n, only if we already know what a of n minus 1 is going to be, or the term before it. When we have recursively defined sequences like these, we need to set a starting point for it. In this case, I'm just going to use 1. So we can't really define the sequence appropriately unless we know where it starts, because we know given the n minus 1th term, we know what the nth term is, but if we never know what a of 1 is, we never know what a of 2 is. We don't know what a of 2 is, we don't know what a of 3 is, so on and so forth. So we always have to have a starting place defined when we have this recursively defined sequence. Probably the most famous recursively defined sequence is what we call the Fibonacci sequence. This is particularly famous because it can be used to describe lots of interesting phenomena in nature and in other places. If you're interested in sort of seeing some examples of how that happens, I would really suggest you do some research, look it up. Things like the golden ratio and the Fibonacci spiral can be really interesting to look at and think about. For now, I'm just going to describe what the Fibonacci sequence is, so we can kind of see another example of how these recursively defined sequences are defined. Right? So for the Fibonacci sequence, I'm going to let f of 0 equal 1, and I'm going to let f of 1 also be equal to 1. And then our f of n, so the nth term of our sequence, is just going to be defined as f of n minus 2 plus f of n minus 1. So you take the previous two terms of the sequence, you add them together, that gives you the next term of the sequence, right? So if we were going to list this out explicitly, we would get 1, 1, and then 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 gives us 13, 13 plus 8 gives us 21, and you can see how the pattern's just going to continue, and will get larger and larger and larger, right? So, like I said before, there's lots of interesting stuff that we can talk about with the Fibonacci sequence, but I really suggest you go and look some of that stuff up for yourself, all right? Cool, cool, cool. So the last thing that I want to talk about is going to be what we call partial sums. So these are going to be listed as S of sum n, S sub n, and it's going to be equal to, and this is some new notation that I'm adding. This is our summation symbol. This is the Greek sigma, and it just means basically add some stuff together. And so we're going to write from k equal to 1 all the way up to n of a sub k, right? And all this means with a summation from k equals 1 to n of a sub k is we're going to take a1, we're going to add it to a2, and then we're going to keep adding together terms of this sequence until we get up to n. All right, so that's all our partial sum is, right? We're taking a sequence A1, A1, A2, and we're adding up together the first n terms of that sequence, right? Oftentimes, we're going to want to write out an explicit formula for what the nth partial sum is going to be. So I'm going to give you an example here of how we can go about doing that. All right, so in this case, we're going to look at a sequence. A sub n is equal to the logarithm, and this will be base 10, of n plus 1 divided by n. All right, and we want to find an explicit formula for our partial sum of up to n. All right, so this partial sum is going to be equal to the summation from k equals 1 to n of our logarithm of k plus 1 over k. And what I'm going to do is we're going to start off by just listing all of our terms of our sequence from A1 all the way up to AN, right? So our A1, actually, let me simplify it really quick up here. So we still got our summation from k equals 1 to n. We've got our logarithm, and we've got our k plus 1. But then using our rules of logarithms, I'm going to use that to subtract our logarithm of k here. All right, so when we're dividing by two things inside of a logarithm, we can represent that as log of one minus log of the other. Right? So our A1 is going to be equal to log of 2, or that k plus 1, where 1 is our k value here, and then minus just log of 1. Our A2 is then going to be our log of 3 minus our log of 2. And then our A3 will be log of 4 minus log of 3. And we can just continue this all the way until we get to our nth term, which is log of n plus 1 minus our log of n. Now, when we take the summation of all of these terms of our sequence, we're essentially just adding all of these together, right? And what we'll notice is that for each term, in the next term, we have something that cancels out. So in A1 and A2, we have a log of 2 and a negative log of 2. Similarly, in A2 and A3, we have a log of 3 and we have a negative log of 3. In our an minus 1 term, which I'm going to write in right here, which is log of n minus log of n minus 1, right? We have the log of n and the negative log of n. This is also going to cancel out with something up here. And so in the end, when we have our total summation of our log of, my apologies, when we have our total summation of the log from k equals 1 to n of k plus 1 over k, the only terms that are left are our log of n plus 1 and our negative log of 1. So this is log of n plus 1 minus our logarithm of 1. But as we know, log of 1 is always going to be 0, right, for any base of our logarithm. So we end up with just the logarithm of n plus 1. So that is an explicit formula for our partial sum, right? Our partial sum is just the logarithm of n plus 1. All right. Yeah, so there's other situations where we can do this as well. There'll be some exercises about it. The final thing that I want to leave you with before I'm done is just some rules of summations, all right? Properties that we have of sums. So the first rule is going to be if we have the summation from k equals 1 to n, and we're taking it of a sub k plus b sub k, right? So we have two different sequences here, a sequence of a terms and a sequence of b terms, and we're taking the partial sums up to n of both of the addition of those sums. That's just going to be equal to the summation from k equals 1 to n of a sub k plus the summation from k equals 1 to n of b sub k. So we can add up all of the a terms first and then all of the b terms and add them together, or we can add them together and then sum up through the terms that we're looking at. Our second rule here is going to be if we have pretty much the same thing, but we're going to have the summation, excuse me, from k equals 1 to n of a sub k minus b sub k. And that's just going to be equal to the summation from k equals 1 to n of a sub k, and then we're going to subtract the summation from k equals 1 to n of b sub k. And finally, our last rule, if we have a summation from k equals 1 to n of some constant c times, we'll say a sub k, that's just going to be equal to c times the summation from k equals 1 to n of our a sub k's, right? So here, a sub k is a sequence b sub k is as well. So b sub k and a sub k are sequences. And c is a constant. And we can just use these rules to manipulate and solve partial sums when we come across problems where we have to do that. All right, that's it for this video. Thanks for watching. Have a nice day.